So I'm going to talk about results from a PRAC award over the past couple of years, talking about modeling of galaxy populations in clusters. Before I give the talk, I need to acknowledge that this is due to a cast of thousands. I'm part of this group called the M-Body Shop, originally founded by George Lake, who sadly passed away just a week ago. But his legacy lives on with many collaborators and in a collaboration with a parallel programming lab at the University of Illinois. And again, lots of collaborators there. And I apologize for people I've missed out on. So just quickly what I'm going to talk about, some background, the computational problem, how we address the computational problem, and focus on some of our results. So let's talk about the motivation. So clusters of galaxies are the largest bound objects in the universe. So what that means is that the galaxies, which in this picture are those little fuzzy blobs, are more fully exploring the gravitational potential in which they reside. The gravitational potential, in turn, is dominated by this mysterious dark matter. In this picture, the dark matter is mapped out by the distortion it produces, gravitationally distorting background light. So this is gravitational lensing map showing where most of the mass is. And then, so we could hope that perhaps these are in hydrostatic equilibrium. This one isn't. This is a collision of two clusters, so it's out of equilibrium. But again, we can hope to use these to explore the nature of dark matter. And this is indeed telling us something about the dark matter. That is, like the stars, in this collision, the dark matter actually passed through itself. So we have an upper limit on what the cross-section of the dark matter is from this object. In contrast, the gas does not pass through it. And so the gas is shown by the pink stuff. It shocks as it tries to pass through itself. And to that point, most of the baryons in this object are in that gas, which is visible in the X-rays in clusters. It's not so visible in normal galaxies. It's just too low a temperature, and we've only recently realized or had direct evidence of where most of the baryons in our own galaxy is. So we have observable baryonic contact. And the other interesting thing about clusters is that related to galaxy evolution. So in galaxy evolution, we have the problem that we need to regulate the amount of gas that turns into stars. One way of doing that is setting up supernovae and blowing most of the gas out of the galaxy. In an isolated galaxy, we could do that in the models at our whim because we just need to get the gas out of the galaxy, and who cares where it goes. In a cluster, it goes into the cluster, and we should be able to observe it. So this puts strong constraints on the kinds of feedback we can have in our galaxy evolution models. So we had this closed box to study galaxy evolution. But there's a computational challenge. In order to study that feedback, we need to resolve down to where the stars are forming. They're forming in giant molecular clouds, which have masses greater than 1 million solar masses. So you need to at least partially resolve that. You need to resolve down to where the central black hole resides in the center of a galaxy, and you need good models for that feedback. You have this multi-phase medium, which you have to model very well, and so you need good hydrodynamics, and there's the kind of particle count that we need to resolve a cluster. And furthermore, in my previous PRAC, I was doing a volume of the universe, 25 megaparsec volume, and it's doing that with a few billion particles. Doing this cluster, basically you have half of those particles are residing in the cluster. So similar number of particles, but they're very centrally concentrated, and this is a very hard problem for load balancing. So just summarizing, the fact that the computation is so clustered introduces these challenges. Only a small fraction of the domain is where you're doing most of your computation. That's the load imbalance. Furthermore, you've got to communicate the gravity from that domain across your entire volume, so there's a large communication cost. And then when the time steps within the cluster are tiny compared to the rest of the volume, and so any fixed costs with doing a time step get magnified. And just so visually, what does this load distribution look like? So in this image, each of these points is not a particle, it's a computational unit, a char, if you were at Mike Norman's talk. So thousands of particles, and what I've colored them by is their computational cost, with the blue being the most costly and the yellow and red being the least costly. So not only are most of the particles in the center, per particle, the cost is much higher. Computational cost is much higher. So if you try to load balance by, say, having equal number of particles per processor, this is what your utilization looks like. So this is utilization of the machine over time, and you can see that the white is bad, right? That is processors being idle. You see there's this long tail of busy processors, and these are at the center of the cluster. And also note that this is showing how we can overlap the gas computation. The light blue is local gravity, the dark blue is remote gravity computation. We're overlapping all that, yet that's mitigating the communication cost, but we have this bad load imbalance. If we instead load imbalance by measuring the amount of computation that's taken and balance that way, we reduce that time step by roughly a factor of 2. And so it's important to do this measurement-based load balancing. The code we do this with is called Changa. This is something I started developing 2003, 2004, many fits and starts. It takes a while, but we finally got all the physics in, and so we're sort of making hay doing the science now. So this is really wonderful, and again, Blue Waters has been a wonderful machine to do it on. This is all built on the Charm++ runtime system, where you divide your computation into a bunch of different objects. I showed you pictures of those objects in that cluster, and these are all running in asynchronously, and it's the runtime that can shuffle these objects around to load balance across, hundreds of thousands of processors. So we're getting very good scaling. This is actually a non-clustered simulation, so it scaled quite easily up to, so this is integer cores on Blue Waters, 500,000 of them. And so with this code, we've run this series of simulations we call the Romulus simulations, and so here's the splash screen for this. So we're in the Pacific Northwest, so we like our black holes to be certified organic, free range, and locally grown. And so the meaning of those buzzwords, let's start with locally grown. So we form the black holes using local conditions of the gas, very dense and cooling on a short time scale. We turn, and low metallicity, turn them into black holes. They're free range in the sense that they are not bound to the center of the galaxy. We have enough resolution that we can actually allow the natural dynamical friction to sink the black holes into the center of the galaxies. This is very important if you're going to think about black hole merger rates. And lastly, they're organic. So for example, the outflow that you see here is an emergent property of the simulation. We just have the black hole dump thermal energy at the center, and this is naturally collimated by the gas in the disk of the galaxy. So we have, in our previous PRAC simulation, we ran a volume, that's the image back here, and what I'm talking about today is the cluster, several clusters, one of which is shown here. So let's take a look at the cluster. So what I have here is just showing on the top row sort of the intrinsical physical properties that we can measure from the simulation. And then on the bottom row is observables derived from the intrinsic properties. So up here we can see the gas density, the gas temperature, which is, in the many millions of degrees. We can combine these two properties and produce an X-ray image. So we can make predictions about X-rays from this cluster. But if you look closely at the temperature plot, you'll see these dark spots. The galaxies are maintaining their relatively cold, as in 10,000 degree gas. As they fall into the cluster, the galaxies are also producing metals, that is everything heavier than helium. And so that's a map of the metallicity. And we can combine these two to make maps of the oxygen 6. So that's 5 times ionized oxygen, which is not hot, warm gas, say 10 to the 5 Kelvin gas. And this we can directly, we're making predictions for new HST observing programs to study how the gas is lost as galaxies fall into the cluster. And then the even cooler gas, this is neutral hydrogen, so around 10 to the 4 degrees, and we can map out, even in this cluster, there are regions where there is neutral hydrogen, which again is an observable that we can make predictions for. And this is all work that Irina Butsky has done and is on the archive. So this is what is happening to the cluster. In turn, the cluster is doing things to the galaxies. And so we have the resolution that we can look at the morphological transformation of the galaxies as they fall into the clusters and understand how a galaxy can go from something like this, a spiral, into these more elliptical galaxies. The red indicating that star formation has been quenched in these galaxies, and we're trying to understand how it's quenched. Is it due to the removal of the gas, or is it due to the operation of the massive black hole in the middle, or combinations of both? So let's take a look at this quenching. So the stopping of star formation. So in the blue, we have a specific star formation rate. So lots of stars being formed, not so many stars being formed. And in the red, on a different scale, is the accretion energy, outflow energy coming from the black hole. And you can see that in the beginning, you see the black hole increases its outflows, there's a dip in star formation. So you have this anti-correlation, but the black hole never completely shuts off star formation, and star formation only really shuts off at the very end, the last 2 gigayears of this particular simulation. So from this, it's unclear whether the black hole fully shuts off star formation, or is there something else involved? And indeed, if you look at go back to the cluster gas, and look what's happening to this. So the red line here is the entropy of the gas in the center of the cluster. I didn't mention, this is the galaxy, the brightest cluster galaxy, thank you, at the center of the cluster. And we're seeing that the entropy of the cluster gas shoots up about 2 gigayears ago. And this corresponds to a merger event. So this total shutdown of the star formation and the raising of the central entropy is actually due to, at least partly, mergers rather than just the central black hole. So that's an interesting result to be submitted. So just sort of summarizing the work the results we can get out of these kinds of simulations, talked about the diffuse gas properties. There's this dichotomy, cool core clusters, non-cool core clusters. What is driving that? And we have some, we think mergers have a great deal to do with that. The evolution of the clusters. Here's an image of the gas being stripped out of a cluster as it out of a galaxy as it falls into the cluster. How does that turn that galaxy into a red and dead elliptical? There's the AGN evolution, including merger rates. Most of the black holes are going to be in centers of clusters. We can make predictions for gravitational wave detectors such as the LISA mission. And then finally, right, clusters are these rulers by which we can measure the expansion of the cosmos. Because they can be seen so far away, we need to understand the internal dynamics of these clusters to calibrate that ruler, and that's where these simulations will play a big role. So, quick takeaways. The clusters are hard for all the reasons that I've mentioned, and there's other reasons that will make them even harder. But thanks to Blue Waters, we're now able to do these kinds of holistic simulations where we have the resolutions to look at the individual galaxies, but we have the capacity or capability of looking at the cluster as a whole. So I really appreciate the time that I got on Blue Waters. I thank many federal organizations for funding what I just talked about, and I want to thank you for listening to this talk.